Today we will talk about two tools, two data transformations in NAND field, in NAND data recovery. It's inversion and XOR transformation. And let's have a look on this picture, which we saw before. And until now, we learned how to extract physical image, how to do page layout automatically, how to apply ECC, and yeah, also how to do the block management stuff. Today we'll talk about those two steps, inversion or XOR, because usually after ECC we need to apply either inversion or XOR transformation. For some very old cases and pretty old cases, there could be a situation when we don't have apply anything. We just can proceed with page allocation analysis after the ECC. So there is no inversion there or XOR transformation. But normally for majority of newer cases, we always have to use the XOR. So let me summarize a little bit. For very old cases, we may not use anything, no inversion, no XOR. For a little bit newer cases, we can use inversion. And for majority of modern cases, for normal cases, we always use XOR. So first of all, let's talk about inversion and what is that and what does controller do and why actually. So inversion, it's a simple transformation when controller just inverts 0 to 1 and 1 to 0. Very easy transformation. And the question is only why? Why would controller do this? And the answer is easy. The empty NAND consists of ones only. So unlike hard drives, empty NAND has ones instead of zeros. For example, when you buy a brand new hard drive, it will be filled by zeros only, and empty NAND consists of ones. It's the thing of the NAND devices. And another thing that user data statistically has more zeros than ones. So there are more zeros. And when it comes to writing user data into empty NAND, we may realize that if we will write original user data into empty NAND, so we will write that zeros into ones, we will have to change state of a lot of memory cells, because we have a lot of zeros. But if we will do that simple transformation of data inversion, amount of data which will be necessary to write to the empty NAND will be much smaller, because originally we have just ones, right? User data has more zeros, like on this area, it's original user data. But after we invert it, we have just, like in this example, just 2 zeros to write. So that ones will not be changed. They will stay like unchanged, untouched, and we will change the state of 2 memory cells only. You may know that controller doesn't like to write data into memory cells because lifespan of memory cell is quite limited. So it's better to reduce writing operations as much as possible. So in order to make that amount of writing operations smaller, controller just inverts data, user data. And with this, controller can increase the lifespan of memory cells. So that's the reason why controller inverts zeros to ones and ones to zeros. So when we unsolder memory chip, data could be inverted there. And to get original data, we need to apply simple transformation to data. We need just invert it one more time. 1 to 0 and 0 to 1. So that's it. So that's the inversion. Now let's talk about XOR transformation. What is XOR? More modern controllers, they use XOR transformation. And what's the point of using that XOR? Because user data usually looks, if you will look in the bitmap to user data, you'll see that user data looks like some patterns. It has some patterns. And modern chips, especially TLC chips, they are weak to store that patterns, to keep of data patterns. And in this area, you can see explanation why. Because if we have some data pattern, like, for example, this, so we have some ones and a lot of zeros around. So that zeros may kind of make some influence of that ones, and the charge may leak from that ones into that zeros. So if we have some group of ones and many zeros around, that ones may disappear. And yeah, like we see on this picture, after some time, there could be some bit errors because of those charge leakage and so on. And to prevent this, controller apply specific, specially designed binary file, which we call XOR key. It applies this binary file with a XOR operation to user data. And after this applying, user data will be converted into such a noisy looking thing. So original user data looks like patterns. Scrambled data, it looks like a noise. And then when we have this noisy looking data, let's say stability of storage will be much better than comparing to not scrambled user data. So it will be much more stable, and data will be kept longer on that TLC chips. So that's the reason why controller would apply scrambling or XOR key. Is this understandable? Do you understand this? Why controller does apply inversion and XOR? All right, so now let's proceed. Now let's see what do we do when we try to convert inverted data or scrambled data back to original ones. So for the inversion, we use inversion element in visual non-tree constructor. It looks like this. Inversion element converts data to the original state, and before we have something like this, so each bit is inverted from 0 to 1 and from 1 to 0. After the inversion in VNR, we have original data. So do you see that here we have example of MBR, looks like. And the same sector, but the same inverted sector looks completely different. So you wouldn't recognize MBR when it's inverted. And the same thing about the FAT tables. Well, actually, visually you can recognize it, but if you will look into the hex view, it won't be visible. So that's the inversion. And now let's see how do we do that analysis, if inversion should be applied or it shouldn't be applied. But first of all, before we even start to check that inversion possibility, We should answer on the question, what's more probable some particular case may have. We should have a look into the dump and check the bitmap. And if in the bitmap we will see something which looks like this, for example, like on this picture, or like this. So we understand that it's not possible this case has the XOR transformation. Once we see some patterns in bitmap, XOR transformation is not possible, because XOR is made to wipe all those patterns, to remove those patterns. And the normal XORed case will look like a noise. Sometimes we may see some patterns which may look like XOR keys. Different XOR keys have different patterns, and here on the last page of the presentation you have some links, and the second link will lead you to the article where you will see some different patterns of XOR keys. Let's open it now here. And that's bitmap patterns of different XOR keys. It may look like this, like that, and so on. So it's pretty recognizable. Well, sometimes it may look like this, like a noise, and in this case, yet you won't see that pattern in the bitmap, but in other cases, it's recognizable. So if you have some case and you look into the dump and you see like 99% just a noise, and just sometimes you see that patterns which may look like XOR key, you understand that this is scrambled data. But if a full dump has just some patterns like this, like that, and so on, so there could be inversion. Okay, so it's done. We make that analysis, and we don't see, let's say we have some particular case, we don't see dump full of noise, we see some patterns. Now the question is, if the case has inversion or it doesn't have inversion, how to check this? We can't do this in the bitmap. We actually may have some ideas. For example, once we found such pattern, we understand that that's probably fat tables, and there should be zeros here, but we see ones, so there could be inversion here. But there is another way. It's a more quick way. We can run analysis, data transformation analysis, and that analysis will check either the dump has inversion or it doesn't have inversion. It will do some hex analysis. It will analyze hex data of the dump, and once it will find inversion, it will show to you the result. If there is no inversion in dump, then it will also tell to you that there is no inversion. Yes, right. The data transformation analysis should be ran on the last element. I mean, you shouldn't add inversion element and then run data transformation analysis. You should run on the element which is right before the inversion. All right, I'll show you in details and explain in details what the data transformation analysis does. Well, actually, I think we will just run the cases now, and then we will switch to the XOR. So yeah, to check if we have inversion, we need to run data transformation analysis, and the utility will tell us if we have inversion or if we don't have inversion. Very easy. Now let's see how it looks like with some case. Okay, I have a case here already. It's the first case. And it's almost solved. There is now just one element here between ECC and the pair. So now we need to do, now we may do several things here. We can just connect it like this. If there is no inversion or XOR transformation, we can use XOR or we can use inversion like this. Oh, I can do this. I need to delete that first. Yeah. So that's the thing we should do here. Now let's check step by step what thing exactly we need to apply here. And first of all, we need to decide what do we have here, most probably inversion or XOR transformation. To do this, I open the dump and I check the bitmap. I just scroll it and have a look. You see that sometimes the dump, like here, for example, it looks noisy. So it looks like a scrambled dump with XOR key, XOR transformation. But if I will scroll it more, I will find a lot of patterns, different patterns. So all those patterns belong to data, user data. It's not possible to have XOR transformation and such amount of patterns and such a kind of patterns, because it would be very, bad XOR transformation if it couldn't delete all these things. So once we found that patterns, we understand that we don't have here any XOR transformation, but we may have inversion. And now how to check this? I select ECC element and I click to data transformation analysis. Let me repeat one more time. I don't do it like this. I connect inversion and then run data transformation, because you people love to do this. It's not correct, because when you run data transformation on inversion element, you run analysis on inverted data already. And if data wasn't inverted, analysis will tell you that it's inverted because it's actually inverted. And you will just connect one more inversion to invert it back like this. So you just run inversion, data transformation analysis on the last element where you suppose it, where you suspect the inversion. And yeah, that's how this window looks like. And what does software do on this analysis? Software is trying to search for these signatures, for these hex patterns, typical hex values, hex words, let's say. Like this is typical for NTFS file system, FAT32, FAT16. This is from boot sector. So software is trying to find these, let's say, grep extensions or hex things. And software is trying to do this with inversion and without inversion. Here actually we have some options what this analysis should search for. So physical image, it's kind of a weird name. This option means that software is trying to search for this for this grep things without any transformation. So if like if there is no any inversion, there is no any rotation and so on, software will tell you that software will understand this, will find that there is no any transformation. The second option is for inversion. So software will try, let's say, if we have it like this. So if we have checked only this thing and this thing, that means that software will try to search for those grep extensions without inversion, with inversion, and without inversion with original data on physical image without any transformation. And that's the main thing here, because another options like unite 2 dumps by byte, unite 4 dumps by byte, it's another transformations, but it's typical for very old devices when we may have several chips, for example, and data was written, was split by 1 byte into 2 chips. 1 byte went to 1 chip, another byte went to second chip. And it could be necessary to unite 2 dumps by byte or 4 dumps by byte, in case if we had 4 chips and controller wrote data into 4 chips by 1 byte simultaneously. So for those cases, we can try this transformation also, and the software will try to search for these things without any transformation, with inversion, and with that uniting. And the same thing about rotation. So some very old controllers used that rotation when it just switched position of byte, 1 byte, of 2 bytes, of 4 bytes. Usually we don't see this. I think in our experience, we saw that transformation very long time ago. Normally we just check that inversion thing. So normally we use this data transformation analysis only for inversion, but by default we may not care about all these things. We can just allow the software for search for this, but most probably it won't find anything from those uniting or rotating things. That's their explanation, which actually you don't really need to know. All you need to know, you just select ECC, click to data transformation, and click to start. Some of you may think that what if the dump doesn't have those grep things? You can add some own extension if you want. You can click here and you can, if you have some specific dump, you can add new signature, and the software will try to search for that signature with inversion and without inversion. So you run it, then you click to the start, and yeah, now it's checking the hex, and quite quick we have some answer. And what do we see here? Found data transformation in ECC 0, and then the what transformation? Actually no transformation. So transformation is no transformation means that there is no any transformation. It means the data is not inverted here. So we just click to OK, skip analysis, yes, because we have actually the answer. There is no any transformation. And all we need to do here means that we just connect it like this, and that's it. We can create logical image and check the data. And data is here. Okay, that's the first case. Now let's see the next one. Okay, here we have two physical images. First of all, I want to check if what is more probable here. I do have XOR or inversion. I open the dump, I scroll it, and I can see a lot of patterns. By the way, maybe some of you don't understand what is pattern. When I say pattern, I mean something, recognizable, some shapes, some pictures, some lines, strings, squares, something like this. This is noise. Here we don't see any patterns, and this is pattern. Here I have some vertical lines. Here I have some another pattern. So this dump full of patterns. And that means that there is no XOR transformation here, but there could be inversion. So how do I check it? I select the physical image. By the way, if I made some decision or opinion based on one physical image, it will be, should be, or must be the true for the second image too, because both these images were used by one controller. So controller applied the same transformations, same algorithm to both chips. And once I found some patterns here, so I decide that there is no XOR here, and of course there won't be XOR in here. And this physical image is actually empty. So that means that this device didn't live long life, and user didn't fill it full of data. Just first image has some data, and second image looks like a brand new. No data was written into second image, but still controller got broken, and somehow we get this case. We got this case. All right, so now let's check the inversion. We selected, click to data transformation, start. And have a look. Found data transformation in a physical image, inversion. Add inversion element to graph, yes. Skip analysis, right. And I have here inversion. In case if I suspect some, let's say, uniting by 1 byte, this is very old case, it may be the truth here. I select both images and run the same analysis here. So now it will search for inversion, for uniting between these 2 bytes by 1 byte. Okay, skip, yeah. Oops. Yeah. So inversion is here. And once I found that inversion should be applied to first dump, of course, I apply it to the second one. I can use this button, copy, and it will create one more element with the same parameters, which I selected. Well, in case of inversion, there is no any parameters, but in case if you have some, let's say, XOR element with a XOR key applied, selected, some things you changed in here in parameters, you can click to copy button, and it will create element with the same parameters like the first one. So it will not be necessary to select XOR key and so on again. There are several questions here. The first one about Linux. As I said, you can add some own signatures in case if you deal with some Linux. you can add some own signatures here, and software will search for the signature that you did add. You can click on this plus, and you can add new signature, some specific signature for Linux file system, and it will search for that Linux thing that you did add. Another thing that there is no ECC element here. We don't have ECC. Well, usually we try to apply inversion after ECC, and we don't have ECC here because it's very old element, very old case, and we do not. Software just doesn't support ECC correction for this old case, and it's not necessary actually, because old cases were really good. I mean, quality of dumps was really good, and it's not necessary to, usually it's not necessary to fix bit errors. There are no bit errors. One more question here. I've got some question from Om, and sorry, I don't understand. What did you ask?
Hi, this is Om. It's like I just want to know that on what basis we have to go for is it for a NAND or an XOR or a inversion. What exactly is the parameter that we need to decide?
Well, actually, this is what I explained in here.
Okay.
Like, first we check if we have some patterns in the dump or if we don't have the patterns. And if we see the patterns, then there is probably inversion. And if we make this decision, we run this data transformation analysis, and it will tell us if we have the inversion or if we don't have the inversion. About the XOR transformation, we will talk a little bit later. Now it's the inversion thing.
Okay, thank you.
Yeah, so we found that there is inversion transformation here, and now I just connected these both elements to the unite, create logical image, and that's it. I can, where is here? Yeah. So the data is here, and you see that it's all green. So PCH is not necessary here. So that's the inversion. And as you can see, it's quite easy to check, quite easy to apply. Not a problem at all, in my opinion, to work with this inversion. Any other questions about this, about inversion? All righty. Now let's move on to the XOR. And what is going on in the utility when we apply the XOR transformation? So when we unsolder the memory chip, it has scrambled data, scrambled noisy looking data. But if we will apply the same XOR key which controller did use for for this case, for this memory chip, we get original data. So the thing is that if we get some data, if we have some data and apply XOR key and then apply it one more time, we get original user data. So 2 times XOR key applied 2 times will create original user data, will give us original user data. So this is how it works. Noisy looking data, XOR key from database, and after this we get original data. And the main question here is what key should be applied and where to take it, because it must be the same. And I mean, each bit must be the same, like controller used. So VNR has a database of XOR keys, and normally we need just to take that key from the database and apply it. And the question is how to check what key to take, which one. Time ago it was not very easy task, because there are many keys with different sizes or different patterns. But now we do have XOR analyzer tool, and it's really easy now to select the correct key. When we want to run this XOR analysis, we need to select some element where we want to check it, for example, ECC element. Then we click to XOR analyzer, and it will ask us if we want to run auto detection. So of course we do want, we click to the yes, and the tool runs this XOR analysis. And I think that I will explain to you what is going on their example. So let me run the case. Okay, so we have the case. Let's check if we see any patterns. And as you can see, most of areas here look noisy. Sometimes we can see this kind of looking patterns, and they are the same everywhere. I mean, the pattern is the same, and it just remains of the XOR key, because you may know that if you apply, or if controller applies XOR key to zeros, it will result just XOR key. So zeros plus XOR key equals to XOR key, and that means that these areas here, the data is just zeros. So user wrote some files with many zeros, and that file was written in this area, and now we can see that zeros, we can actually see XOR applied to that zeros. But majority of data, most of data here looks like a noise. Okay, so now let's see how do we apply the XOR key. Now, first of all, maybe I'll show you quickly the old way, the manual way of XOR key selection. So to select the XOR key, you need to bring to the workspace the XOR element, connect it like this. And then you go to here, to parameters, open, and select in the XOR key for controller. You select the XOR key by several rules. First of all, you select it by controller name, and then by page size, and then by size of the key. And the size of the key shouldn't be equal to, I mean, here, size of the key in pages. It shouldn't be equal to the block size of the particular case, but it must be multiplied to this. It means that, for example, in this case here, the block size is 256 pages. And the thing is that the XOR key applied usually to whole block. So the binary file of XOR key is equal to one block, usually, but it's not always, because it could be like this. Let me draw you one thing. So let's say that this is our dump. Do you see what I'm drawing here? Okay, and why? Yeah, now you should see. Yeah. So let's say that this is the dump, and here we have one block, next block, and so on. So XOR key could be applied to whole block. So let's say that block size here is 2 megabytes. So XOR key size could end 2 megabytes and 256 pages. So XOR key may have size 2 megabytes or 256 pages. Or there could be situation that a XOR key has size 1 megabyte and 128 pages, and controller just did apply XOR key, one XOR key 2 times to one block. So there is one key here and one key here, like this. So when I say that key size, XOR key size should be compatible to the particular case, that means that the size must be the same to the block size of the device, or it should be multiplied. For example, if the block size is, in our case, block size is 528 pages, this XOR key will be compatible. This XOR key will be compatible. But if we'll find XOR key with this block size, 258 pages. Oh, sorry, I meant this, of course, 512 pages. So for this block size, this XOR key is compatible, this XOR key is compatible, this XOR key will not be compatible. So yeah, it must be divided. XOR key size must be divided. I mean, block size must be divided by XOR key size. So when you select some XOR key, you have here that list. It starts from controller name, and then here in that commas you have first page size, 8K, 8K, 4K, 4K, and so on. It means 4 kilobytes, 8 kilobytes, and so on. And then size of the XOR key in pages. And you need to select some of these. For example, for this controller, you can type PS2251. And 1, 2, 3, 4, 5, like many XOR keys we have for this one, and which one to select. It could be not very convenient, let's say. And now we have that XOR analyzer. And now let's see how it works. How it works like. So I have ECC element. I didn't see any patterns, like user data patterns. And now I want to run XOR analyzer. I select it, I click to XOR analyzer. It says to me, start auto detection. And I click yes. And it did something now. And it's quite, it would be good if you understand what actually did it do. The thing is that I told you already, oops, let me share the presentation. I told you already that when we apply XOR key to zeros, we get a regional XOR key. That's the first thing we need to remember. Now let's see what does software do when we run XOR analysis. Software is trying to find same blocks within whole dump. So software will tries to find blocks with the same content. It just compares all blocks within the dump and then shows us the table, this table, and blocks which have same content, same data, will be brought to the top. So software will try to find same blocks. That's the first thing we need to remember. Second thing, let's think what blocks in the regular dump, normal dump, will have what data, what kind of data will be in the same blocks within regular dump. I mean, let's say that we have some dump, we have several blocks with the same content, same data, exactly same data. And what data most probably will be in that blocks? And when I say same blocks, I mean like absolutely same, bit by bit. Like absolutely equal blocks. And it could be not empty blocks. It's not empty blocks, but blocks filled by zeros. Usually, all cases have some blocks which filled by zeros, because that zeros file system writes to the device. And normally, from our experience, we have found that if we will analyze regular case, normal case, we will find several blocks which will have the same content, and usually that blocks have zeros inside. Of course, it could be some another blocks. Of course, it could be some, like by some coincidence, some user data blocks which have same content. But normally it's zero blocks with the same content. And how do we search for that blocks with the same content? We just take, by default, we take 3 random position in each block, like 1 block, 2nd block, 3rd block. We take 3 random position, totally random positions, and we read values from that positions, hex values. And blocks with the same values most probably will have same content. And then we will get such a, okay, guys, do you hear me now? Hello? Okay. Because I've got a sound like headphones were disconnected. Okay, so then let's proceed. After the test, we get the table, and in this table, each line represents 1 block. And here we have physical address of the block. Then we have a column with values, and that values actually from that test positions. So we took, by default, we take 3 test positions, and then we compare the test positions from all the blocks, and blocks with the same values will be brought to the top. And we can see it here, like here we have 81, 83, 46, 1, 2, 3, 4. 4 blocks with the same values. So that means that most probably content of that blocks will be the same, since these 3 values are the same. And it's not like 100%, but probability is very high, and you'll see this later. And the signature, it's the first several bytes, first 3 bytes of the block. We call signature, well, we use this word signature for XOR keys, and it's a start of XOR key, first 3 bytes of XOR key. So let's say that if, for example, this block or this block has just zeros, and XOR key was applied to these zeros. So as a result, we will get on the first 3 bytes in that block signature of our XOR key. It will be the same like a signature of a XOR key. Okay, now let's see how it works in the software. So let me run auto detection again. You see it's going quite fast. And that's the list of blocks which I mentioned before. So in here, in this area, I can see bitmap. Source bitmap means that I have here bitmap of the selected block here. So you can see that when I switch blocks, the content here is changed. So here I have blocks, here I have bitmap of selected block, and in here I have list of keys which most probably will be compatible to this particular case, to this specific dump. And if I will switch this tab from source to the result, I will see actually a result of this selected XOR key applied to this one selected block. And as you can see, for example, this key can XOR first half of the block. So here I have 1 block. I can use this zoom in, zoom out thing. So first half now looks like zeros. Second half still looks like a key. So this key is, let's say, half compatible to this particular block. And the same for another ones. What if I try another key, for example, this one? You see that it's pretty the same, right? This one just shows noise, so this key is not compatible to this case at all, because as I said, I suspect to see here, after applying XOR key to the selected block, I suspect to see here some pattern. And usually this pattern is zeros. In most of cases, it's just zeros. Then next, and this key seems to be good, because you see that the whole block here now looks like zeros. And actually, I can do this analysis. I can check all these keys automatically. I can select some block, for example, this one. And I have here a button validate key. So software will try to apply this key from this list to the selected block, and the key which will show best result will be brought to the top. For example, this key has 99.99% of efficiency, let's say, because after applying this key to this particular block, software checks entropy, and if entropy is low, that means that the key did good job, and we don't have any noise after this, so that means that the key is good, it's compatible. We can select some another block, for example this one, and you see now the its result is smaller because there are some data here. So the best scenario case, we need to find here a block with the zeros only, and then run key validation on this block. And after this, we have this key, which is highlighted, which has the checkbox, and it's very easy now to apply it. We need just to click to apply XOR, and that's it. So now we have the XOR key, XOR element with selected XOR key. I connect like this, create logical image, and no file system user. So everything is available now. How do we create this list of keys? How do we create this list of the keys? So we have a filter here. You see in this window, we have a filter, and we insert. So if we like remove everything from here, so now we have full list of all keys available. And basically you can run this validating on all keys, but it will take like a really big time. So we apply some filtering things. And how do we filter these keys? First of all, we filter it by page size. So we apply two page sizes here. It's the page size which we actually do have here, 8640, and you know, some keys, actually most of keys, they apply it for data area only. So the XOR key size which will be applied to data area only in case of 8K page size will be 8192, right? So that's the page size. We filter all the keys by page size. And second thing which we use here for filtering, it's a signature. Do you remember that signature? It's the very first bytes of the key. And we can see that signatures in each name of each key. And where do we take the signatures? We actually take them from here. So we take all these signatures from each block and we insert it into this window. And there is quite a big chance that, as I told you, we have 0 blocks here in the dump, and that 0 blocks will produce more or less pure XOR key, which will have, which we will see signature here on the first position. So let me run auto detection again. And again, as you can see, we get the list. Now it's a little bit different because each time the test positions, test indexes, these ones these positions. We take them randomly. So after one scan, we may have one blocks. After another scan, it could be another blocks. But statistically, usually we have here blocks on the top with the zeros. Okay, now I can click validate key again. And that's it. I have good looking pattern. And this block is even better. So the common scenario here would be like that. You run auto detection, then you suspect, and then you hope that you have blocks with the zeros here on the top. You select some block which you feel that has zeros. For example, you can click to the source and you see this pattern, and you're familiar with this pattern already. You know that XOR key pattern looks like this pattern. So great, you have a XOR key pattern. Once you found such block, you can run that validating here. After this, you check result, and that's it. Usually it all works automatically. We check this on many cases, and normally result is, you can get result within several clicks. But sometimes you may be required to perform another scans, more scans. And that more scans should be performed with another block size. So by default, when we run this analysis, we divide physical dump by blocks which are equal to block size from the configuration, from the structure. Like usually it's virtual blocks or logical block size. So we divide full dump by logical blocks, and we take 3 test positions from each block. We compare them and we bring them the blocks to the top. But sometimes, let's say that we have just one block with zeros within whole dump. There is just one block. And in this case, we won't find this block, right? Because software will take 3 test positions from this block. And if there is just one block with zeros within whole dump, we won't be able to find similar one. But there is also quite high probability that XOR key, one logical block, has XOR key, 2 XOR keys inside, like on this like on this picture. One block has 2 XOR keys. And what can we do? Like we just suppose now, we suspect that there could be a case here. And for such cases, for those cases, we may try to apply next trick. As I told you, by default, we use logical block size. And this size is here. And it divides whole dump by these blocks and test these blocks with these text indexes, test positions. But if we didn't find anything on first step, let's say we don't see these blocks, we can try to divide. We can like just guess, suspect that what if one block logical block has 2 physical keys. It's a quite regular case. We can click to this button, and now software will analyze each 1 megabyte. So one block size will be like 2 times smaller than it was before. And now if we run auto detection, software will select new text indexes and have a look. Now test block is smaller, but amount of these blocks is bigger, because before this one line represented one bigger block, 2 megabytes block. But in fact, that 2 megabytes block had 2 keys inside, 2 XOR keys. And when we divided that block by 2, now instead of 6 probable results here, we have already, sorry, instead of 4 or 3, we have much more. So you can use this divide thing only in case if like first try didn't work. But as I said, normally it works automatically from the first try. The question is, you mean same 2 keys or different keys? Well, of course, if the controller is only one in this device, and of course the controller use the same key. And the thing is that the controller used 1 key, like the key which has size 1 megabyte, to the block which has 2 megabytes. So it used the same key 2 times to 1 block, like on that picture. So yeah, same key 2 times. But you know, it's a theory and it's a background. It's good if you will understand what is going on background, but normally it's not necessary. Normally you just follow this scenario, like you make first click, second click, then you get this window and you select several blocks from, you select some good looking block from this list, and it's usually on the top, and then you click to validate key, and you will get the answer which key is good for this case, which key is not good for this case, very quick. Okay, now let's see the next case. That's actually quite interesting. It's no name SD. So let's say that this is some monolithic device, SD card, and we don't know controller name. Well, we can guess if we open the bitmap, we can see noise, noise, noise. So no any patterns. But then when we will scroll the page like this horizontally, we can see this pattern. So it can give us some idea that that's the SM controller, right? But anyway, we don't know model name, and if it comes to select correct XOR key, we will have quite big, you know, variety of XOR keys which we can try, and it will be hard. But with this new XOR analyzer thing, it could be really easy to do. So let me just click to XOR analyzer, start auto detection, quickly I get a list of blocks, and you see that now this block and this key gives me something, but it's like not very clean. It has some patterns. Maybe I will try next block. And you see that this block, next one, it shows me better picture. The thing is that usually from the very beginning, I have more or less compatible or good result from the block and plus the key selected here. And then to proceed, do you hear me, guys, or it's just Amarbir? All right. So, and then to proceed, we need, as I told you, to select some combination where we will have more or less good result. So we will have to select some actually block, which we suppose has some zeros. And in this case, this first block, you see, it's not that good. It has some patterns, and I wouldn't take it. Then the next one seems to be much better, but as you can see, that first half of the block is good, second half is still XOR, but probably it happens because they're not very compatible XOR key. So once you found block which you suppose most probably is the good block to test the keys, you click to validate key. So basically, after the run auto detect, after the auto detection thing, you need to select some block where you'll see more or less good result. Test block. And just within several seconds, you will see that all these keys not good at all. This one is 50% good. This one is 99% good, but the size of this key is not compatible to this case because this case has 256 pages and the size of the key is 258 pages. So it's for another case. And this block is, and this key is totally compatible. You can see that I have just a zeros now. If you can't find good block for testing here, for example, you try it and you can't realize which one would be good to test, you can run here auto validating. And the software will just try to apply all those keys to the selected block. So you select this block and it tried all these keys through this block, then next block. And probably it's the way to go for you if you're not sure which block to take. Maybe after some time with some experience, you see which block will be good, which block will be not good. And you select it first and then you run validating. But if you don't have any clue which one to take, you can just try all of them one by one until you will see here some more or less good result, high result. Like this one. And so you see that it's even for no-name controllers, when you don't have any ideas with what the controller name inside, you can find XOR key very quickly and very easy. And once you found this, you click to apply XOR. It's here, connect. And now, do you remember I told you the option copy? You can use this option for this XOR key. You don't need to like drag and drop new one, select same XOR key and so on. You can just click to copy and you get the same key right after this. So then you create logical image. Some data is corrupted, probably it's necessary to work on markers table. Yeah, but here all pictures good. Let me try to repeat here that think about block size and division here. So again, by default, we take for analysis logical block size. And in case if you didn't find anything here, you can try to decrease it. If you suspect that this case, for example, we have here block size 256 pages, right? But XOR key size could be 128, for example. So you just click to this button, or you can basically put any size here, but it's like automatic one. So you click to this button, then run auto detection. And if before we had approximately 3 blocks with that keys, so now it's 1, 2, 3, 4, 5. You see, now we have much more results because each block was tested 2 times, and since first half of the block is equal to the second half of the block, then we just then we get 2 results here, 2 strings, 2 lines. That's the thing of that block size. However, once again, as I said, usually you don't have to play with this. You just click auto detection and then validate key, and that's it. Okay. Any questions for this case? All right, then let me proceed with the new one, next one. Next one is a U controller. I think you saw this controller before. And very same steps. ECC, XOR analyzer, auto detection, and yeah. From the very first step, we see some good result. I click to validate key. And have a look, guys. I have here 4 keys which are totally compatible for this controller, for this case. Why? Because block size here 384 pages, but it seems that XOR key with a size 128 pages was used 3 times for this one block. So that's why this key is compatible, 128 pages applied 3 times to one block. This key is compatible, this key is compatible, the same, and even this key is compatible. Software takes 256 pages for the first 256 pages of the block, and then 128 pages, and since they are the same, so we get good result here. The same will be for the next block. And so we select, for example, this. Key, apply it, and there you go. logical image, and so on. File system. It doesn't work. I need to run ECC correction. And now it should be fine. The question is, on the left side, the block with the most zeros will present first. Yes, statistically, they will be the first. Well, actually, on the left side, we will have on the top blocks with the same content. What we do here, we compare content of each and every block, and blocks with the same content will be on the top. And usually, that blocks with the same content have zeros inside. If you will write, let's say, some test case and fill it full by sevens, so you will get sevens blocks with the 777 on the top. So on the top, you see blocks with the same content. Usually, that blocks have zeros in like normal, regular cases. Okay. Also, there was a question about XOR key extraction. We will do another webinar for this, but if you really want to do this right now, I can just show you direction how you can do this. This case will be better. So you can do this very easy with this XOR analyzer tool. Let's say you don't have any XOR keys here, so but you understand how XOR key pattern may look like. So all you need to do here, you need just to select some blocks with XOR key, and here you have several options like first clear all use, and then these two blocks have the same, and it looks like this. Each block has two keys inside, so because we have pattern, we can see pattern 2 times within one block. So we divide it by 2, click to read values. So now we have more keys. Now I'm just checking that binary is all the same. So clear all use flags, and now I just select 3 of these blocks. Yeah, right click and extract selected blocks. And I have 3 blocks here, and if you're familiar with the XOR key extraction, you will understand what to do with these 3 blocks. So with this element, it's very easy to search for blocks with XOR key and to extract that blocks. And then you can proceed. You can use the bit verify thing for these blocks data area and so on and so on. All these things in details we will discuss on one of next webinar, where we'll talk about unsupported devices. All right. Now the SanDisk case. The same steps: XOR analyzer, auto detection. And now, interesting thing here. You can see that these blocks, they look like some patterns, so it's probably good blocks because these patterns looks like XOR key looking pattern. But here I don't have any key, and it happens because of the filter here. If you remember, we filter all XOR keys by the things, by these rules in here, in this filter. And what rules do we use? We filter it by default by page size and by signatures. And those signatures, it's first three bytes from the XOR key. And we take these signatures from the blocks from this list, which we found. But the thing is that you will get exactly same signature here, like XOR key has, in case if first 3 bytes of the selected block will has just zeros. So zeros plus XOR key will be the XOR key. But if you remember, SanDisk starts from service area. And even though content of this block is just zeros here, service area, first several bytes of service area may not be zeros. And that not zeros will produce another signatures for the SanDisk controllers. So that's why the signatures will not be compatible to any of XOR keys that we have in database, because first several bytes of SanDisk, we may not have just the zeros and first several bytes of service area. So that's why for SanDisk we need to use a little bit another approach. First, I will remove all that signatures from the filter. So now I see all keys with a compatible page size. And second, I can use another filter. For example, I can filter it by vendor. I can type here SanDisk. And now I have just several keys here, which I selected by the vendor and by page size. And this block seems to be a good one for testing because I have some recognizable pattern here. So I click to block sorting, block validating, and this key seems to be a good one. I switch it like this, and that's right. I can see many zeros. That means that this key seems to be good. And as I told you, you see this first bytes. It's not zeros only, there are several bits with the ones. So that's why signature was wrong. Signature wasn't compatible to this one. You see, signature of this key is actually C6, 34, C7, and here we have 34, C7, but first byte it's F6, and here it's C6. So it's all happens because of this one bit, I believe, or several bits here, no, several first bits. And that's it. Yeah, that's their good block, that's the good key. Then you again click the reply key. You get it here. Connect it like this. And there you go. Create logical image. And it's done. I think ECC should be on. And here is the data. So again, some SanDisk controllers, they have peculiarity to another ones, which should be taken into account. Okay, that's basically everything I wanted to tell you. Just the last thing I want to mention, it's a dynamic, Phison dynamic XOR. So there is one peculiarity for devices with Phison controller. Usually it's micro SD cards or some SD cards that there are two types of XOR keys, static key and dynamic key. In case of static key, that binary which is applied to the data is the same all the time. So one static key is applied to each and every block. In case of Phison dynamic XOR, controller will generate new XOR key for each block. And that's why it's not possible to extract it from the dump, since each block will have different key. And there is only one way to XOR this case, it's to create this dynamic XOR, dynamic key on fly with the utility. The good thing that there is just one algorithm. I mean, for majority of Phison controllers, there is just one algorithm of that generation, and we have it. And the only thing you need to do for that keys, it's for the devices, you need just to bring this Phison dynamic XOR key element to the area, to the workspace, and after this, you need to apply one more XOR key, which is already normal one, static one, because on the diagram, data transformation, when data is written to the NAND memory, looks like this. We have original data, then to this original data, static key is applied, and then on this result, dynamic key is applied. So when we do reverse operation, reverse transformation, we need to apply first Phison dynamic XOR and then normal XOR. And on a real case, it looks like this. Open case. So there is physical image. We apply BCR because there are bad columns here. Then we apply TCC correction. And then, since we know that this is Phison controller, there could be, and this is micro SD card, there could be dynamic XOR. Also, if we run normal XOR analyzer here, we'll not see any good result. There are some two blocks with some noise, and you see that all looks very noisy and very different. So this analysis will not work. We will not have any keys proposed here and any good blocks. And it all happens because the dynamic XOR. So when should you think about dynamic XOR? When you have micro SD or SD card usually, and when you suppose that this is Phison controller. How can you understand that this is Phison controller? First, you can just have a look into the page structure, and you can see that we have data, then service area, ECC, like here. No, it's undefined here because it's defined on ECC element. So data, service area, ECC, and so on. So page structure may tell you that this is Phison. And of course, when you run ECC, you will get the answer that code word. Well, you don't know that this is Phison. You will run search code words by all vendors, and after some time you will get the answer that this code word is compatible for the case. And since this is PS, you understand that this is Phison. Okay, that's the Phison, that's the microSD. XOR analyzer doesn't work, so probably there could be dynamic XOR applied. And dynamic XOR doesn't have any parameters. You need just to apply it, so you don't change key position. The only thing you need to do here, you click on this skip empty areas checkbox, because if you don't click here, this element will apply XOR to empty areas, to data areas, and it will just confuse you later. I mean, like now, you see these lines. That's the XOR key applied to empty areas. And if you enable this, XOR key will not be applied to empty areas. So gray areas, empty areas stay just gray. There is only one thing here you need to check, you need to make sure about. It's the block size, virtual block size. Because when you read memory chip, like when you do physical dump, you click to read NAND ID, you get the ID, then you read it, and then you have some structure here. And you have block size, which is like 2 megabytes approximately here. But logical block size could be different. It could be 2 times bigger. I think we will discuss this in details on next webinar, why it actually happened. It's because of multiplane page allocation. And in case if that multiplane page allocation was used here, you will see that, so the block size here is the 258 pages. But then if you will check it in service area, you will see, oh, by the way, that's interesting case here. This case has 2 planes. This device has 2 planes. That's the first plane, that's the second plane. And you can see that the service area presents in first plane only. So we have here some service area, then some pattern, which is the same all the time, and then next block. So by default, we had a block size like this one, 258 pages. But in fact, block size will be here like 516 approximately, 516 pages approximately, because that's the first plane, that's the second plane, and both of them belong to the same logical block. There is an article on our website about this, and you can read there more examples about this. There is a link for that article in PDF file I gave you. So yeah, you can learn it. And that thinks about why we actually have here 2 physical blocks within 1 logical block. We will explain on the next webinar. So to sum up, all you need to do with Phison Dynamic XOR, you need to check that your block size is correct, virtual block size or logical block size is correct, because by default, logical block size is equal to physical block size when you read the chip. But logical block size could be bigger, 2 or 4 times, like in this case. And then you need to adjust it. You need to change it. For example, here in structure, your block size was 2 megabytes. And then I think on this step, it was changed to 4 megabytes already. That's the PDF file. Okay, so but now we're talking about XOR, and to reply Phison dynamic XOR, you just bring this element to the workspace, and then on this element you can run XOR analyzer. And you see this case is more tricky because blocks with the same content here now on the top, but that blocks, they actually don't have zeros. So probably now it's time to try that option I told you before when we try to decrease size for analysis block size 2 times, like this. And now run auto detection again. Okay, again, we don't have some good result. Another approach here that we may use, we have, you see, just 3 keys here. Yes? 2 for Phison controller and 1 for some, not for some SK controller. And we can see here that signatures. So we can try to apply XOR key. We can try to find block with this signature and apply XOR key for that block. So we have here like 50, 61, something, right? So I can arrange blocks by signature and I can search it. And yeah, it's not good. Ah, no, it's this block. Okay, let's check this now. AF and something. Yeah, this case has more complexity. But anyway, it's possible to do. For example, this block, you see, I found it now and it produced me as a result this block plus this key. I have just zeros. If I click to validate key now, I have 99% that it's a good key. So what happened now in this case? I didn't have many blocks of zeros. So that blocks software didn't bring to the top. And I had to search for good blocks for testing manually. I did that by signature. I checked signatures here and the probable keys. And I searched then that blocks in the list, the signatures. And one of those blocks, you see, for example, this one, not good because it's just several bytes. We have here zeros, but then it's full of data. The same about, I don't know, this block is good, for example, it has zeros. This one not. So sometimes it could be a little bit more complicated, but still it's much easier than just to search for such pattern within whole dump and then try to apply block XOR key for that pattern. Another thing that you sometimes may use, it's this adjust key to page layout. I think, but you will use this only when you use like a manual. If you manually open some key, and then you will have to click to this adjust key to page layout button. In another cases, you don't use it. So basically there are just two options here which you can use. It's skip empty areas and adjust key to page layout. Adjust key to page layout option is made for XOR keys which have size, which are applied to data area only. Here you have some example of page structure. It looks like a Phison controller page structure. When we have data area, then service area, ECC, and so on, several periods. And in this case, only data area is XORed. So we can see that it's XORed, then service area and ECC is not XORed, and so on. And the key for this case, in case if it's 4 kilobyte page size, its original key it's 4332 bytes, but the key will have size 4096 bytes. So it will not have that service areas and ECC areas, because it's a universal for all. It will be universal for all 4 kilobyte page sizes, because different controllers may have different models, let's say, may have different size of service area of ECC, and we don't do XOR key for all types of pages, all size of pages. We do one universal XOR key, which has size 4096 bytes for data area only, and it will be compatible with all types of 4 kilobyte pages. And when you click to that adjust key to page layout, all the software does, it just insert zeros for this key where you have service area and ECC. So it transforms like this. And then you will get a compatible key for this specific page size with any ECC or service area. So that's the thing that adjust key to page layout does. And you need to use it only when you're selected manually XOR key from a database, because if you run that automatic search, like we did, for example, once you found it here, that's the key, you click to apply XOR key, you get it here. So all the options selected already. You have skip empty areas, you have adjust key, and that things you don't worry for now about. So that's the parameters of XOR key.